Well, so we continue with our discussions regarding the phase equilibrium, which we had already started in the last lecture. So therefore, where did we stop? We stopped by defining the vapor liquid equilibrium under ideal conditions. Before that, I had already mentioned to you that the if we just refer to the to what we had just done, we had ended up here from where we can find out yi as a function of xi. And normally when we are dealing with vapor liquid equilibrium, if you see that for this particular state your yeah, for a vapor liquid equilibrium in distillation, we find that the number of components, suppose it is a binary mixture, then in that case the number of components, say it's 2. Just let me see, the pen has been highlighted. Yeah. So for this particular case, we find even for a binary mixture, the total degrees of freedom, that is equals to, for 2 components we are having 2 C minus P plus 2, which gives you 2 minus 2 plus 2, which is equal to 2. So therefore, normally what happens, if we know 2 number of intensive properties, the other properties can be found out. So by convention, what we have, we either know T and X and we can express P and Y, or maybe we know P and X and we can express T and Y. In this particular way, we can find out the vapor liquid equilibrium under different conditions. So therefore, we find out that for Pxy data, if you find that just now we had discussed that Xi Pi saturated equals to Yi P, which automatically means that the P, it is a linear function, the pressure varies linearly with the composition in the liquid phase, as a result of which we find that P versus x1 it is linear and P versus y1 is something of this sort. Above this we are having a liquid, at higher pressures there is liquid, at lower pressures there is a vapor. The corresponding Txy diagram can be developed from here, and we find that in this particular case, suppose we start with a liquid here and we start heating it, then the first bubble it appears here. So therefore, this is known as the bubble point curve, and in the same way, if we start from the vapor phase and if we start cooling it, then we find that the first dew appears here, and this particular dew, it is in the dew, the composition which is in equilibrium with this y corresponds to the horizontal line, which is the isobaric isothermal line. Right. Even from here, the vapor which is in equilibrium with this can be obtained from this equilibrium line, and these particular lines, if you remember, you must have studied them in thermodynamics, they are known as tie lines. And based on these correspond to the equilibrium compositions, and they can be plotted, and once they are plotted, we get a graph something of this sort. There is something which I would like to remind you, that these particular for these particular graphs which have been drawn, the one component, it refers to the more volatile component, and as a result of which we get the y versus x curve in this particular form. Right. Now, suppose the solution is not an ideal solution. Under that condition, what we do, this is applicable for the liquid. For the vapor phase, always the solutions are ideal. So, for the liquid phase, when the solution is not ideal, we modify the Raoult's law, or rather the Lewis-Randall rule, by incorporating a parameter gamma, which is known as the activity coefficient. Now, there can be positive deviations from Raoult's law, there can be negative deviations from Raoult's law. In other words, gamma I can be less than 1, gamma I can be greater than 1. When gamma I is greater than 1, naturally the pressure, the total pressure is higher than that calculated from your ideal solution model, and when it is less than 1, natural total pressure is lower as that computed from the ideal solution model. So, quite naturally the Pxy, Txy and the Xy diagrams, they get modified for non-ideal solutions in this particular way. This corresponds to the negative deviation from Raoult's law, which forms the maximum boiling azeotrope. At this particular, when we find that the two boiling points are not very much removed and the deviation is quite high, for such conditions we find that the Pxy exhibits either a minima or a maxima. Corresponding to that, we find there is one particular composition where the mixture boiling point is much higher compared to the boiling point of the pure components, and this point it refers to the maximum boiling azeotrope, which forms when there is a negative deviation from Raoult's law, and we also have, for positive deviations from Raoult's law, we have a minimum boiling azeotrope. Now, these azeotropic conditions, they are very useful for finding out the gamma. That is why I would like to mention special reference to it. Now, for non-ideal solutions, what we find? We find for non-ideal solutions generally it is written at gamma I xi fi 0, this is equals to yi into p, and for low to moderate pressures this corresponds to pi sat, and so therefore again this gamma i's that has to be found out from the other available parameters, and normally there are some activity coefficient models, you must have studied them in your thermodynamics. Here I would like to mention that mostly for finding out gamma I, the models which are taught in the colleges, they are usually the Van Laar model and the Margulis model. But in reality, when we try to find out gamma I, then in that case we use some models which correspond to the NRTL model or the Wilson model or maybe the Uniquec model. Usually we use these models which normally we do not cover, but you remember that these are the models which are normally used, right. And at the point of azeotropy, what happens? Xi becomes equals to yi. So, under that condition we find that gamma I becomes equals to p by pi sat. So, therefore, finding out activity coefficients at the point of azeotropy, it becomes extremely easy, and therefore, it is very important to determine whether we are going to have an azeotrope for two reasons. Moment we have an azeotrope, we cannot perform further separations by distillation, and at the point of azeotropy, we can estimate the gamma I, right. So, therefore, this was the vapor liquid equilibrium, and I would also like to mention that it is not only that we find out yi from xi. Conventionally, very frequently what we do, we can often express the vapor liquid equilibrium data in terms of some equilibrium ratio which gives the ratio of yi by xi. For this particular case, we find this will correspond to Pi saturated gamma I divided by P, right. And there is also one other thing, we find that this Ki naturally, since it is a function of Pi saturated, which is again a function of temperature. So, naturally the Ki, it is a function of temperature, it is a function of pressure, and it is of course also a function, it is also a function of composition. So, therefore, very frequently instead of expressing the equilibrium data in terms of Ki, very frequently what we do, we express it in terms of a parameter which is expressed as alpha ij, which is the ratio of the two Ki's for in the two particular phases, and for vapor liquid equilibrium this is known as relative volatility. It simply shows the ease of separation of the two components, and you will find that very frequently the equilibrium data, they are expressed in terms of alpha ij, right. And once alpha ij is given, from this particular equation for a binary mixture we find this corresponds to yj is nothing but equals to 1 minus yi, xj is nothing but equal to 1 minus xi. Therefore, this is for a binary mixture. So, therefore, for a binary mixture what we find is that alpha ij, once it is known and you know your xi, then you can find out yi the way I have substituted, you can do it out. You can find that alpha, this corresponds to, so therefore, for any xi you can find out yi once alpha is known by using this particular formula, where this alpha it corresponds to gamma I pi sat by gamma j pj saturated, right. So, therefore, the ratio of Ki for the for the different components, they can be expressed in terms of the relative volatility for a vapor liquid or a gas liquid equilibrium data, and accordingly we can express it in this particular form. Conventionally, Ks are used for ideal solutions, and when a solution is ideal, you have already studied, they are ideal for adjacent members of homologous series and for isomers, etc. So, therefore, the K values they are available for hydrocarbons. So, typical K values which are available have been shown in this particular slide, where if you know the pressure, if you know the temperature, then for the different hydrocarbons you can very easily find out the K values. Once you can find the K values, you can find the alpha values and you can generate the vapor liquid equilibrium data. For other substances, as we go into distillation, you will find that quite often we give you the data on alpha, right. And there can also be some situations where you will find that the equilibrium data either in terms of Txy or in terms of xy are available. When that is there, then you can use that as well. Just in passing, I would just like to show you this, we will be doing in much more details when we do distillation, that how does pressure affect the Txy data. What do we find in this particular case? We find, if you observe carefully, you find that more or less the difference between the bubble point and the dew point, that becomes narrower and narrower as we go for higher pressure conditions. In this particular case, these are for higher pressure conditions. When this becomes narrow, what it means? It means that the relative volatility between the two phases, they become closer, and therefore separation by distillation becomes more difficult. Also, you will find that once we exceed the critical conditions of the more volatile component, then we find that the curve becomes looped, and therefore, the range of conditions where separation can occur by distillation, that becomes smaller and smaller. So, these things, the effect of pressure on VLE data is something which we will need to remember when we decide upon the pressure in which we would like to operate the distillation column that we are going to design. Well, so after that, the next thing which I wanted to tell you was that, see, when we were dealing with vapor liquid equilibrium, we had assumed that all the components, they exist in the liquid phase over the entire range of compositions, right. And then what we did, we assumed the ideal solution model, and then we modified the ideal solution model, fine. So, therefore, if we consider the modified form of the ideal solution model, this was the solution. Finding out Fi0 was not at all a problem, because this just corresponds to the pure component fugacity at the temperature and pressure of the system. So, therefore, if you know the temperature and pressure of the solution, you can very well find out Fi0. This will correspond to the saturated vapor pressure at low temperatures, or else you can very well find it out once if you know FIV and also the Poynting correction factor, you can find this out. It is not a problem. Suppose the liquid is in equilibrium with non-condensable gases, right, which means that at the condition of the solution, the gas does not exist as a liquid. If that is the case, then in that case this Fi0 for the non-condensable gas, that becomes a fictitious state, and finding out Fi0 becomes difficult under that condition. This is the case which we encounter for the process of absorption. So, what do we do? See, we have to find out Fi cap for the liquid phase if we at all have to calculate the equilibrium conditions. Unless we can calculate the equilibrium conditions, we do not know that if suppose we want to remove carbon dioxide from air and we add water, whether at all any removal will happen or not, we have no idea. So, by some means we need to find out, maybe if it is carbon dioxide air in contact with water, then when we need to find out FCO2 in the water phase or the liquid phase, we need to find out FCO2 in the vapor phase, and then we need to compare to find out whether at all we can do absorption or not. For the vapor phase, it is not at all a problem. We know that it will either be equal to pressure, or in other words it will be equal to phi CO2 into pressure depending upon the composition. It is not a problem. So, therefore, how to find out this? If we do not, we cannot find out FCO2 in the pure state. So, when we refer to the graph of the partial this fugacity with composition, we find that the just like at very large compositions, Fi is proportional to Xi and the proportionality constant is Fi0, we find that at very low compositions also, under this condition also, Fi that is proportional to Xi, but the proportionality constant, this is not equal to Fi0, but it is the Henry's law constant. So, therefore, for absorption we can very well write down that Fi in the liquid state, that is equals to Hi into Xi for an ideal dilute solution, or if it is not an ideal dilute solution, we are going to modify it by activity coefficient, where this activity coefficient which I have denoted with gamma I star, that corresponds to the deviation from the ideal dilute solution model, right, and this will be then equal to YIP. As a result, here Yi can be found out by gamma X star Hi by P, which reduces to at low to moderate pressure, this becomes Hi Xi by P, and therefore, Ki for absorption process, which is Yi by Xi, this is equals to HIP for the case of absorption, and therefore, we find that for and accordingly you can find out alpha ij or whatever it is for the case of absorption in this particular case, right. Well, accordingly, once we can find out Yi and Xi, definitely for different Xi's we can find out Yi and we can start generating the data. But as I have told you that conventionally we express the data in terms of partial pressure and Xi. So, therefore, in order to do that, we find that Pi in this particular case, this corresponds to Hi into Xi. So, once you know Xi, we can generate the partial pressure data, and we can find out, rather we can generate the Pi versus X data for different conditions. Here the Pi versus X data has been shown for hydrocarbon solubility in polyalkene glycol. This is just a typical curve, and the same thing exists for different situations as well, right. Now, for this Pi versus X curve, which correspond to absorption equilibrium curves or the vapor liquid equilibrium curves when a non-condensable gas is in contact with the liquid. So, for these particular cases, how does the measurable parameters influence this? How does pressure influence the Pi versus X curve? When we increase pressure, quite naturally the solubility increases. So, therefore, with application of pressure, the solubility increases. How does temperature influence? See, with increase in temperature, if suppose any particular process is there which liberates heat, then in that case the rate of the or rather that process, it becomes slower as we go for higher and higher temperature. This is from Van 't Hoff's law, we know. So, therefore, for most of the absorption cases, they are accompanied by release of heat, or in other words they are exothermic. Therefore, for most of the cases we find that as we increase the temperature, the curve becomes more and more steeper and the solubility of the gas that decreases with increase in pressure. Then we also find that these particular absorption equilibrium curves, they are also a function of the type of gas that is there. They also depend upon the type of gas. And I would like to mention in this particular case that when a mixture of gases are brought in contact with the liquid, say for example, when we have ammonia, pure ammonia which is contacted with water, and we generate this particular curve where the ammonia, and in this particular case naturally it will be the pressure of ammonia and in contact with the water, right. Again, suppose we have ammonia air mixture and we contact it with water and we try to generate the curve. If we find that we express the equilibrium curve in the terms of Pi and Xi, then we find that if the ammonia is mixed with some particular component which is sparingly soluble in the solvent, then in that case when we bring ammonia air in contact with water, the Xi, it remains almost constant, it does not change, and therefore, if the same equilibrium curve can be applicable whether we are dealing with a pure component or with a component in a mixture with some other components which are very sparingly soluble in the solvent, provided we have expressed it in terms of Pi. Also we find that suppose there are a mixture of a number of gases, all of which are soluble or a number of which are soluble in the solvent, then under that condition we find that we can use the equilibrium curve for each particular solute, provided all of them form ideal solution with the solvent. If they do not form ideal solution with the solvent, then definitely you know that the Henry's law constant changes, and under that condition we cannot use this Pi versus Xi curve. But we can use this Pi versus Xi curve for any component I if the other components along with I, they form either ideal solutions with the solvent or they are almost insoluble in that particular solvent. Also it is important to note that suppose in the solvent, say there is a non-volatile solute dissolved. For example, in water suppose we add some salt. Quite naturally under that condition also this particular equilibrium curve is not going to be applicable under that particular case. And just as an example, I would like to tell you that suppose we have propane and butane, right. Both of them, they can be absorbed by say light hydrocarbon oil. Now, for this particular case we find that in this, since each of the component they form an ideal solution. So, therefore, for propane also if we have this Pi versus Xi curve, that is going to be applicable for pure propane as well as in this particular mixture. The same thing is also true for butane as well. But suppose we have a mixture of ammonia and say methylamine, say for example. and I am absorbing it say in water. In this particular case, the equilibrium curve generated for ammonia or ammonia air, that is not going to be applicable for a mixture of, or rather for absorption of ammonia in water in presence of methylamine. So, therefore, these are the few things that we need to remember, and usually this is the reason why normally we express the absorption equilibrium curves in terms of, in fact, I would like to tell you that whenever there is a gas phase, we always prefer to express the concentration in the gas phase in terms of partial pressure, be it absorption, be it gas solid adsorption. We usually prefer this, right. So, now the next thing is, after absorption, after adsorption, the next thing which I would like to discuss is AD adsorption, right. So, in adsorption and in extraction, what happens, that we will be discussing in the next class. Thank you very much.